Hey, so we're welcome to the Friday morning session, and for the first talk, we're very happy to have Shai Ben David from Waterloo and the Vector Institute, and he's going to discuss well, some quite surprising connections.
Okay. So I'm kind of an outlier in this workshop, but I am talking about meta-mathematics, but I'm talking about meta-mathematics applied to machine learning. And what I'm going to talk about is some improbability and impossibility results of basic problems in machine learning. So let me start with a very kind of short introduction to how I see statistical machine learning. So with statistical machine learning, a major problem is the following. You have some unknown probability distribution. Say this is the environment. And you see a sample from that distribution. So you see a sample the environment generates. So say you see some patients and you assume that they are generated by some distribution. And this is the empirical data. And you're trying to, given the sample, you're trying to learn as much as possible about the sample generating distribution. So you may want to learn the structure of the distribution, or you want, or this is distribution over binary valued classification. So you want to learn the classification. But in general, what you want is to learn as much as possible about distribution just based on this sample. So the first two questions to ask are, what prior knowledge does the learner have? This is my computer. What prior knowledge does the learner have? And the other is, what does the learner wish to deduce about this underlying distribution? So the most ambitious framework is you say, I have no prior knowledge, and I want to learn everything about the distribution. So I have no prior knowledge. What does it mean to learn everything about the distribution? What I want to do is to get an approximation of the distribution without any prior knowledge. So that would be the most ambitious thing, no prior knowledge. I want to learn everything. And not surprisingly, I mean, that's kind of the schema of what we're doing. There is an unknown distribution. It generates some samples, and we are trying to learn what the distribution is just based on the sample. But not surprisingly, such an ambitious task is probably impossible, and it's very easy to see why it's impossible. So just consider a discrete finite domain, say of size n, and if you have a sample size which is less than square root of n, then we know that it's unlikely to see any point appears twice. But if no point appears twice, then you have no clue whether this data was generated from a uniform distribution over the whole domain or from a uniform distribution over some subset that includes all of the data points. Or in other words, if I'm running a lottery and I want to cheat and I collect random 10,000 draws of the lottery, and now instead of running the lottery, I'm just drawing from my 10,000 collection, as long as I will not see, nobody will see repetitions, you will not know that I'm cheating. So this is without prior knowledge, we cannot learn what the distribution is. So this brings us, so if we want to be samples, the sample size, we want to be independent of the domain size. In most cases, domain size is very large, practically infinite. Okay, so it brings us two kind of important types of restrictions. So one of them is we assume something about the distribution. We assume that the distribution comes from a restricted family. So that's kind of what I call a prior knowledge. So let's say we assume that the distribution is a mixture of Gaussians. Then we have a chance of figuring out what the distribution is. So either we introduce some prior knowledge, or we say we don't want to find out everything about the distribution. We just have a collection of queries about the distribution that we want to be able to answer. So these are kind of two directions in which we can diverge because we cannot do everything at the same time. And I will talk about both problems, but in this talk I will mainly focus about the second approach. but I will also have something about say something about the first approach. So, so the focus will be a characterization of learnability. What can we tell about a distribution when we don't know in advance, we don't assume in advance what type of distribution we have. Okay, so the kind of model that we want to follow is the very strong results that we know for binary classification. For binary classification, if all you want to know is learn the binary rule, then we know that Vapnik and Chavonenkis practically solved this problem in the 70s. The VC dimension tells you whether a class of binary valued function is learnable or not. So the question is, can we get similar results for more general learning problems? Okay, so the outline of the talk that I will mainly describe impossibility results on the topic of what can we learn about distribution without prior assumptions. And I will show that this question, the answer to this question is independent of set theory. So that's kind of a surprising connection between logic and machine learning. And that's joint work with Pavel Rubes and Shai Moran and Amir Shpilka and Amir Yudaev. I will also talk shortly about a very recent impossibility result about the other type with my student Tosca Lertner. We showed that if you want to know which classes of distributions are learnable, so now we go to the other direction. We assume that you know that your distribution comes from a certain class. Can you learn the distribution? If you want to know which classes are learnable, we just showed in the last months that there can be no dimension that characterizes which classes of distributions are learnable and which not. But I will mainly focus on the first result to a large extent because this is not published yet. Okay, so a general approach to learning is uniform estimation of random variables. So if I have a collection of queries that I want to know about a distribution, I can view them as random variables. Each answer depends on the distribution. It's a random variable. So I have a collection of random variables. And the simplest approach to learning about the answers to these random variables is the uniform convergence. So what does it mean? You get a sample that's generated by an unknown distribution, and you want to estimate the expectation of every query in your collection of queries. That's called a uniform estimation. We estimate the expectation of each of the random variables in my collection. Or I have a collection of queries. I want to estimate the answer simultaneously to all of them. And this is well understood. And this is the uniform convergence. And uniform convergence is really characterized by the VC dimension or some other dimensions of the class of queries that you want to ask. So, but that's a kind of a very strong goal. I mean, you want to be able to estimate the answers to all of the queries. And in many cases, we settle for something milder, which is what we call expectation maximization. So what is expectation maximization? If I have a collection of models, it's not that I want to estimate the error of each of these models. I just want to find one model that is close to optimal. And I don't care about estimating the expectation or the success or the error of all of the models in my collection. So that's what I call expectation maximization. So we have a collection of real valued functions or queries or random variables over some domain X. You get an IID sample generated by some unknown distribution, no assumptions about the distribution, and you want to output some H in H that has as high as possible expectation with respect to P. So rather than estimating the expectation of all of them, which is characterized by the VC dimension, we just want to find a good one, and we don't care about the rest. That's expectation maximization, and this is clearly a kind of a not harder problem. We'll see immediately it's really an easier problem. So many problems in machine learning can be cast in terms of this expectation maximization. If I want to find a binary classification predictor, I can say each predictor has an error, which is the expected error of this predictor. And I don't care about the error of all the predictors. I just want to find a predictor with minimal error. So that's kind of expectation minimization, which is the same as expectation maximization. And the same if I want to learn multi-class, not necessarily binary, or if I want to find the best case center clustering or whatever kind of clustering for a distribution. I have a distribution. Every k-tuple of centers is a model. I don't care about estimating the expected loss of each of them. I just want to find a k-tuple that gives me a result which is close to the optimal objective. So many problems, and the list goes on, many problems that we attack in machine learning, they can be cast as expectation maximization. So what I'm saying is that the approach of uniform convergence that is so common is kind of an overkill. We need less than that. So we want to characterize this expectation maximization. When is this possible? So the tools that we usually use, I just list some common tools in machine learning because we're going to discuss connection between them. So pack learnability means that you want to have a sample size that guarantees that you are epsilon close to the optimum with probability higher than 1 over delta. So it's the 1 minus delta. So it's probably approximately correct. There is learnability with empirical risk minimization that says all you do is you look at the sample and you find the model that's best for the sample, and that's the model that you output. And there is weak learnability, which says rather than being able to approximate the optimum to arbitrary precision, you just fix some threshold and you say, I'll be happy if I can approximate the optimum to 0.3. And there is uniform convergence, which we already mentioned, and there is existence of sample compression schemes that I will talk about in a minute, and there is the finiteness of combinatorial dimension at the VC dimension. The nice thing is that when we talk about binary classification, all of those are equivalent. A class is pack learnable if and only if it is weakly learnable, if and only if ERM will learn it, if and only if you have a compression. All of those conditions are equivalent when we talk about binary classification. The problem becomes more difficult. So binary classification is the easy case. The fundamental theorem of machine learning, statistical learning, says that the class is all the above is equivalent, and this equivalence holds even in terms of also quantitatively. If you know one of them, you know the numbers, you can calculate the numbers for all the rest. Anyway, we already in 2010 with Amit Danieli and Sivan Sabato and Shai Shalev-Schwartz, we showed that this equivalence break down even when you go from binary classification to multiple classes. So assume that now you want to classify not just into 2 classes, but into 10 classes or to some number of classes, then this equivalence already breaks down. We showed that there are multi-class classes for which empirical minimization algorithm.
Sorry, I don't understand. Yes.
Yes.
So what does it mean that different empirical risk minimization algorithms? So I guess what does it mean that the algorithm
Different
it's a different algorithm, but they have the same, they achieve the same result?
No.
You said.
So okay.
So they minimize the risk or?
Okay, empirical risk minimization means you look at the sample that you got,
Okay.
and you pick a model that minimizes the error on the sample.
Right.
But what you care about is the error over the distribution.
Yeah.
So in binary classification, if you can have 2 different models that have the same error over the sample, but they can have different errors in the redistribution. In binary classification, if you have any model that minimizes the error over the sample, you know that it will be good for the distribution. That's generalization. But when it comes to multi-class, you can have different models.
So this you show by example?
What?
This you show by exhibiting some such cases?
Yeah, we show by exhibiting cases. I mean, we show that there are algorithms that minimize the error over the sample, but they don't generalize. Whereas in binary classification, if you minimize the error over the sample, you're guaranteed to generalize.
You also see that in practice, I think you run a deep network and you can get to 0 training error, but you need to continue to get to generalize.
Right, but that's what happens in deep neural networks already covered by the theory of uniform convergence.
And even then, in practice,
In practice, you see differences. But here it's in theory, we show that there could be different algorithms that minimize the error over the sample, and one of them will generalize very well, and the other one, although it minimizes the error over the sample, will fail over the distribution. And that was a surprising result at that time. Okay, so the corollary is that when we generalize from two-class problems to multi-class problem, this nice equivalence, already some part of it fall apart.
So how large must be the output values, like the?
Okay, so that's a good question. So the gap between different ERM algorithms is a factor of log k, where k is the number of classes. But you can also consider a situation when you have infinitely many classes. Say you want to learn a real valued function. And then it can be complete failure for one ERM algorithm and good success for another ERM. But the factor is log k, where k is the number of classes. Yes.
What is the size of the sample? Maybe you need a bigger sample that it won't happen or something like that?
No matter how big the sample is, you will still fail. There is a kind of an ERM strategy that no matter how big the sample is, you will keep failing. So no, I mean, all those questions are really in place because this was really a surprising result. And okay, so what I want to focus for concreteness, I mean, we are talking about the Emacs problem. We want to have the expectation maximization. So let us be more concrete. So let us focus on the case of subset probability maximization. So what do I mean here? So H is a collection of subset of X. We have some unknown distribution, and we want to find which subset has the highest probability. Which subset in my collection has the highest probability or close to the highest probability. Again, rather than estimating the probability of hitting each of the subsets, I just want to find one subset that has close to maximum probability. So in this case, it is already shown, it's easy to see that the equivalence breaks down, because if H is the class of all subsets of some infinite domain, then the set of all subsets of an infinite domain has infinite VC dimension. So we know by Vapnik-Chervonenkis that we will not have uniform convergence. But if I ask you, give me a set that has maximum probability, you know which set it is, all of X. So you don't even need any samples to answer the maximum probability question, but you won't get uniform convergence. So this is a very simple example where finding the maximum probability element in your class is much, much easier than estimating the probability of each of them. Okay, so in this case, uniform convergence fails because we have infinite VC dimension, but Emacs learnability is trivial because you know that the highest probability will be to, if the whole domain is one of your subsets, you just output the whole domain. That's in my next slide. Okay, so what happens? So we want to kind of classify, characterize when a collection of subsets or a collection of random variables is learnable. When can you guarantee that you will find the one close to the one with the maximum probability? So, and we want to have a combinatorial characterization. Okay, so what I will go now, I will soon talk about finite, the collection of all finite subsets, but I want to introduce the main tool. And the main tool is compression schemes, and compression schemes, they go back to Occam, saying that the shortest the explanation, the best. What? Oh, this is running without my control. Okay. So what are, one manifestation of the Occam razor is the sample compression scheme. It was introduced by Littlestone and Varmuth in '86. And so what are compression schemes? So compression schemes, we can think of it as a game between Alice and Bob. I'm borrowing the Shafi, Silvio, Alice and Bob terminology. So
You said borrowing.
no, borrowing.
It's comparing.
Sorry. Okay, so Alice knows everything. She knows our family of models, and she knows which model the data came from. And Bob knows only the family of models, but not which model the data came from. And then Alice gets a sample from this, that is, the model D fits this sample. And Bob only knows the whole family. She passes some small subset of the sample to Bob, and Bob needs to reconstruct a good approximation to the model just from this small sample. So that's sample compression. Alice got the whole sample. She is allowed to pass to Bob only a few points from this sample, and we hope that he can reconstruct a good approximation to the model that generated the data. That is sample compression schemes. And we say that the class of models has a compression of size t if they can have an agreement between them that will allow Bob to always reconstruct the answer by just getting t of the samples that Alice got. So this is sample compression scheme, and Littlestone and Varmont introduced sample compression scheme called binary classification, and they show that if you have a compression scheme, then it's learnable. And Moran and Yehudayev, exactly 30 years later, showed that the other direction is also correct. Every learnable class has a finite compression scheme. That's the binary classification case. Okay, so for binary classification, packed learnability is equivalent to existence of a sample compression scheme. So now in our problem is that we want to do this Emacs problem, and the Emacs problem is different. So we came up with a notion of sample compression for the Emacs problem. I don't think it's important to read the technical details. I will demonstrate this sample compression scheme for the simple case of collection of subsets. So for a collection of subsets, and we show that the existence of a compression scheme is equivalent to learnability. For a collection of subsets, so let me explain to you what is the compression scheme for the collection of subsets. So the collection of subsets, say we look at all the finite subsets of some domain X, and there is a distribution. We don't know what the distribution is. We generate a sample. We want to find the subset or a subset that has as much as possible probability. So Alice gets a finite sample, and she is allowed to pick only a small subset of the sample to pass it to Bob. And Bob needs to find a subset eta of S prime, and we want to guarantee that this eta of S prime is close to having the maximum probability. And so that's kind of the game that we are playing. Can we have a game in which there is an unknown distribution over finite subsets of some domain X. I'm Alice, I'm getting a finite sample. I'm passing to Amos a small sample. He should be able to reconstruct. We want to reconstruct a sample that is a superset of S. So because we want to have something with maximal probability, if the sample is S, you will work well if you can reconstruct a superset of S. So let us play this game. This is a kind of a very, yes.
Alice knows what the distribution is.
Alice knows everything, right? Alice knows everything. But the problem is that Alice just got a sample S.
And she can only transfer a subset of those.
Right, a small subset of those. And it will suffice for learning. We showed it suffice if Bob can reconstruct a superset of S.
So why don't you pick the maximum?
Okay, so you're running ahead of me on time, one slide ahead. So let us see when this game is doable and when not. So if X it depends on the cardinality of X. If X is finite, it's trivial. Because if X is finite, then Bob has to answer with a finite subset of X. So Bob can only answer with X, all of X. It sure will be a cover of the sample. What happens if X is countable? If X is countable, so say the natural numbers. So Alice knows the distribution of the natural numbers. She gets a finite sample. She has to pass to Bob only a few of them, and he needs to come up with a set that covers the finite sample. So what will you do with the countable domain? Take the maximum element, and Bob will say, here is the initial segment, it's a finite set. And it covers the sample because it was the maximum element of the sample. So it's very easy if it's countable. What happens if X is uncountable? Then it becomes interesting. So now our game is as follows. I mean, our domain says the real numbers. Alice gets a finite set of real numbers. She has to pass to Bob only few of them, and Bob has to recover a subset of real numbers that is a superset of the original S. How can they do it? So for the real numbers, it becomes really challenging. What? A well ordering will work, but
All possible extensions of that.
yeah, but if you take an initial segment of a well ordering of the reals, it's not going to be a finite set. Bob has to output a finite set. Sure, I could take a well ordering of the reals, repeat the idea of a maximum element. Bob will give the initial segment, but it's an infinite set. Bob has to come up with a finite set. So it becomes difficult. So the main combinatorial result that we showed is that if you have finite subset of X, there is a compression scheme of size K if and only if X is less than Aleph K. So this is a kind of a new characterization of the cardinals Aleph K. I mean, I mean, I'm enjoying it even when I'm telling it for the 100th time. So what is, just let me remind you what are the Aleph Ks. So the Alephs are the infinite cardinals well ordered. So Aleph null is the cardinality of the natural numbers, and each Aleph n plus 1 is the first cardinal that's larger than Aleph n. And the Cantor theorem tells us that the real numbers are greater than Aleph 0, but the Paul Cohen famous results of the continuum hypothesis tells you that you cannot prove what exactly is the cardinality of the real numbers. This is independent of ZFC. So it could be any of the Aleph Ks. It could also be above all the Aleph Ks. We cannot even prove whether it's one of the Aleph Ks or it's above. But now we can go back to our problem. We said in the previous slide, we said that, previous slide, yeah. We said that you have a finite compression scheme of size K if and only if your domain is less than Aleph K. So now I'm playing the game over the reals. And I can win the game over the reals if and only if the cardinality of the reals is one of the Aleph Ks, which is independent of set theory. So we show that the compression game is independent of set theory, we can do it or not, but the compression game is equivalent to Emacs learnability. So we get that the Emacs learnability is independent of set theory. So let me say something about the proof. So am I going backwards, forward? Okay. Okay, so just to say something about the proof of this nice characterization of the Aleph Ks, if I want to show that if X is less than Aleph K, then you have a monotone compression of size Ks, we can do it by induction of K. So think of it as, say that the reals are Aleph 1. How do I get a compression scheme? So I take a real ordering of the reals such that any initial segment is countable. Now Alice gets a sample. She gives me the element which is maximum in the sample, but of course I cannot give Bob the initial segment because it's countable. But then I look at the rest of the sample. Now it's countable. I can map it to the natural numbers, and there is a maximal element in the mapping to the natural numbers. So Alice can give just 2 points. One of them tells you which countable ordinal covers all of the sample. And the second element that Alice gives tells you, once you know it's a countable ordinal, you can map it to the natural numbers, take the maximum in the natural numbers, it will give you a finite set. So if the cardinality of the real is aleph1, you can do compression of size 2. And similarly, you can do compression of size k if the cardinality of the reals is aleph k minus 1. And we can also show the other direction. Well, we can also show, oh, I see what my problem is. Each time I'm turning it like this, so the forward and backward switch. Okay, so we can also show that the other direction, that if you have a compression scheme of size k, then the cardinality cannot exceed k minus 1. Okay, so we get this result. Now we don't need anything so smart as Ramsey, but we need playing some games. Yeah. Okay, so because Ramsey would have given us bigger gaps than just one. Okay, so for the Emacs learnability, we can show that the following is equivalent. So we said Emacs learnability is find just the model which is close to the best. And for Emacs learnability, we can show that PAC learnability, I mean, you want with probability 1 minus delta to find something which is epsilon good, is equivalent to weak learnability. That is, if you can give me something which is 0.3 good, then you will be able to give me something which is arbitrarily good. And this is equivalent to this monotone existence of this monotone compression scheme. And so if we go over the equivalence that we had before, now we just have the equivalence of the blue guys. And we were left with the question of, can we find a dimension that will characterize Emacs learnability? We already know that Emacs learnability of the set of all finite subsets of the reals is independent of set theory. Independent of set theory, whether it's learnable or not. But we still can ask, can I find a dimension that characterizes it? And now we use something more sophisticated in set theory in order to show that there can be no dimension. But in order to show that there can be no dimension, I need to define what I mean by a combinatorial dimension. So the definition that we took here, okay, we also have a quantitative version, which I don't think matters so much. Well, where are we? I'm not sure if I'm going backwards. Okay. Okay, can we find a characterization? So the question is, what do I mean by characterization? So a combinatorial characterization, I mean that we have a first order formula that quantifies over members of X and over members of H. If you recall, what is the visit dimension? The visit dimension says there exists, this dimension is D, if there exist D points such that every 0, 1 labeling of these points is realizable by one of the H's in H. So we have, there exist X1 to XD in X, and there exists H1 to H2 to the D in H, such that they realize every combination. So we say, define a dimension by having a first order formula that quantifies over X and quantifies over H. And you want that the dimension will be such that a class is learnable if and only if the dimension is finite. So we know that we have it for the visit dimension, and many other dimensions like fat shattering dimension, the graph dimension, Nautron dimension, many dimensions that have been discussed, all of the dimensions that we know from machine learning, they all fall into this pattern of a combinatorial dimension. It's a first order formula with quantification over elements of the domain and over elements of H. Okay, so now we show that you cannot have such a characterization for the learnability, for the Emacs learnability. So here we used a kind of a tool from a forcing technique. So if you have a submodel and both are models of ZFC, when we do forcing, we start with the model of ZFC in which some statement holds. Then we go to a submodel of this in which the statement fails, and both of them are models of set theory. So if I have M0, which is a submodel of M1, and both satisfy ZFC and both share the same domain and the same class, then any finite characterization, the truth value of any such formula is the same in M1 and in M0. If I have a formula that only quantifies over elements which are common to both models, first order formula, it will be the same value in both models. So what it means is that if we have a finite characterization, then when we go between different models of ZFC, I ask you, is H learnable? The answer in one model of ZFC will be the same as the answer is the other model of ZFC, because the characterization is limited enough to not change between the models. So I jump to the corollary. Anyway, so we can construct two models of set theory in which the reals are the same, in which finite subsets of the reals are also the same, but in one of them, the cardinality of the reals is above Aleph omega, so Emax fails. In the other one, the cardinality of the reals is one of the Aleph Ks, so Emax succeeds. So I have two models of ZFC in which every characterization will give me the same answer, but in one of them, this class is learnable and the other is not learnable. Therefore, I prove that I cannot have a notion of dimension that characterizes this Emax learnability. Okay, so that's the conclusion. There could be no finite character notion of dimension that characterizes Emax learnability. And it's worthwhile thinking. I still want to talk about the other direction as well, but let me just have a comment here. It's worthwhile thinking, where is this independence coming from? Because we're talking about weak learnability. I just want to learn up to approximation 0.3. And I have finite samples. Where is this independence sneaking in? And the reason is that when machine learning, statistical machine learning is defined, it's defined in terms of learning functions, not of learning algorithms. When we talk about a learner, you want a function from samples to models, but there is no requirement that this function is computable. If this function were computable, then every program will be a finite element and there will not be this type of independence. So it brings about a point that was not really nobody paid attention to before, that there is a gap here in our definition of learnability and the nice characterization, because we didn't require that the learners must be computable. So if we learn as computable, we will not get such an independence. And we embarked on this direction of what happens to classical machine learning, even binary classification, when you require that the learners must be computable, must be programmed. So this is a series of works with students of mine. We defined learnability in terms of requiring computable of the learner, and we showed that the VC characterization of binary valued functions fails. So already in binary valued functions, the characterization by Vatn-Chevonenkis collapses if you require the learners to be computable. And also in recent work with another student, Nikki, we showed that the characterization of online learning of Littlestone collapses if you want the learners to be computable. So it's kind of the undecidability came from the fact that we did not require in the definition that learners are computable. So let me finish with the result in the other direction. So as I said, there were two directions. One of them, we restrict the collection of distributions and ask, if you know the collection of distribution, can you tell me which one is the model? The other one, you don't restrict, you do distribution free, but you only ask certain questions. So that was about the second problem, this independence. With the first problem, so the question of characterizing which families of probability distributions are learnable, it's been open for 30 years. We just showed with another student of mine, Tosca Lechner, that there can be no notion of dimension that characterizes learnability of finite domain distributions. So if you ask the following question, I mean, in a previous work, for example, we showed sample schemes that for learning mixture of Gaussians. So we know that if you know the distribution is a mixture of Gaussian, I give you a sample, you can approximate it well. But there was still the open questions, mixture of Gaussians work well. which distributions, which families of distribution will not work. Can we find a dimension for this? And we show that there can be no dimension for this. And the technique is completely different. Let me just explain it on the board. So what do I mean, no dimension? So if we talk about dimension in sample complexity in learning, we talk usually about this function, which is mh of epsilon delta, which means number of sample size required to epsilon delta learn, to get precision epsilon with confidence at least 1 minus delta. So this is the sample complexity function. And if we have a dimension, we know that for every h, mh of epsilon delta is actually a function of the dimension of h and epsilon and delta. All that you need to know about the class is the VC dimension. If you know the VC dimension, you know the sample complexity as a function of epsilon and delta. So a dimension, in some way, it captures all the relevant information from your class H. So what we showed is that if the classes is classes of distribution, of finite distributions, there are too many behaviors to be captured by just a natural number. There are too many behaviors to even be captured by just a real number. So there can be no dimension that once you know the dimension of the class, you will know what is the learning rate for that class. Just because there are too many behaviors and you cannot compress them into just a single number. Okay, so these are my impossibility results for today. Thank you.
Okay, questions?
Let me start. Actually, I have two questions. So one is a bit more technical. So there's this other definition of learning where the learning rate can depend on the function being learned. So does this still hold for this?
You want to talk about what we call non-uniform learnability. I don't think we have time to look at it. I mean, this is kind of the last few weeks that we got this result.
Okay, and the other question is, so you convinced me that combinatorial learning theory has nothing to say about learnability. Right, that's what you showed. That you cannot say it, but in the real world, machine learning is making big strides. So, is this theory actually relevant for anything?
So I think that I tried to, in some way, answer it by saying, in real world, machine learning are programs. The learners are programs, and once you have the learners as programs, you don't have this independence. But the downside is that once you have machine learning as programs, then also the nice characterization that we all know, accept as a truth from God, breaks down. So we get the advantage that nothing is independent of set theory, but we are really just making first steps in understanding characterization under computable functions, computable learners, which is the realistic situation. Yes.
If the learners are algorithms, then X is supposedly countable.
Right. So in order to talk about algorithms, you have to encode X. And yeah, so you have to encode X and you have to encode.
If it is countable, then there is no independence.
No, right. No, I'm saying if you require the algorithms to be learnable, to be computable, then there is no independence. That's what I'm saying.
Yeah, but a stronger statement is that if you require X to be countable, then there is no independence.
If you require X to be countable, then it's not, I mean, this independence result will not work for countable X, but there could be, H could still be uncountable, and the class of all learners could be uncountable. So it's not obvious that for countable X, you will not get independence.
No, but you can define models of real computation. And there are actually several competing models of real computation that can be done.
Can you show again this main characterization with like the number of samples and the cardinality?
Oh, yeah. So that was the okay. That's right. So yeah, if your domain, we're talking here about the collection of finite subset of X. So X has size less than Aleph K, if and only if you have a compression scheme of size K. And that's a clean new combinatorial categorization of the Aleph Ks in terms of a finite game with finite outcome between two pairs. Yes.
Okay, for this last result, would you be able to get the characterization if, for example, I'm thinking about the support of these distributions, like if they're only supported on a countable set with rationals or something?
That's all about countable support.
That's kind of
Because each distribution has even a finite support. But the collection of we talk about class of distributions. So you have many classes of distribution. Every class of distribution is countable. But we're talking about characterizing whether a class of distribution is learnable or not. So you want this function D to be a function from all classes of distributions. So yeah, the negative result already holds for distributions over finite subset of the natural numbers.
More questions? Okay, so let's thank Shai again. We adjourn at 11 a.m. for 2 more talks.